Yesterday we learned the Pythagorean theorem. It was not presented in if-then form, but we could say it that way and say if we have a right triangle, then a squared plus b squared equals c squared. That's what the Pythagorean theorem says. Remember we talked about yesterday that it's important that we consider that right triangle part of it because it's only true for a right triangle. So if we have a right triangle, then we have a squared plus b squared equals c squared. Today we're going to talk about our converse to the Pythagorean theorem. We learned what a converse was a very long time ago. A converse is when we switch the if and the then. So the converse of the Pythagorean theorem would say, if a squared plus b squared equals c squared, then it must be a right triangle. Converses are not always true, but it turns out that the converse of the Pythagorean theorem is true. So that's what Theorem 8.3 says, is if the square of one side of a triangle is equal to the sum of the square of the others, or if c squared equals a squared plus b squared, then the triangle is a right triangle. So we can use this to test, given three numbers, if those three numbers would make a right triangle or not. There are a few sets of common right triangle lengths. We call them Pythagorean triples. They're common because they're nice, clean numbers. They end up with no square roots in them. 3, 4, 5 is the most common set of those. And we could multiply that by anything we want as long as we multiply all the parts. That's just going to create a similar triangle, like a blown up version of it. All the angles would be the same, it's just that we're kind of doubling all the lengths to kind of blow up the picture. So we could multiply that all by 2 and make it a 6, 8, 10. Or multiply it by 3 and make it a 9, 12, 15. Multiply by 4, you can multiply by 5, you can multiply by 10, you can multiply by anything as long as you multiply all of them. Another common one is a 5, 12, 13. That comes up frequently. The other two, I use the word common a little bit loosely. We don't see them tons, but they'll come up every now and then. And when I say these are common, I don't necessarily mean like in actually making things. If you're going to make something that has a right triangle in it, you could definitely use these numbers. But I don't know that people often set out to use these numbers in making things. They're common in the sense of in math. They're common. Particularly in math textbooks, homework assignments, tests, and especially standardized tests like plan tests, ACT, MME, SAT, those types of tests. Love to use these numbers because they work out cleanly. Okay? So you'll see these a lot on those types of standardized, like multiple choice type tests that will end up with triangles that have sides of 3, 4, 5, or 5, 12, 13. You do not need to memorize these. You don't, because you could always just apply the Pythagorean theorem. So if you're given a picture of a right triangle and it has a 3 and a 4, you could just do your Pythagorean theorem and you'll end up finding out that it's 5. However, if you learn to recognize them, that will save you a significant amount of time, especially on those timed multiple choice tests like ACT and MME where time can be really important. So don't feel like you need to put these on flashcards and memorize them, but if you can learn over the course of doing problems to recognize them, then it will be a time saver for you. Along with the converse of the Pythagorean theorem, there's kind of two more that say, well, what if that doesn't happen? So the converse of the Pythagorean theorem said, if c squared equals a squared plus b squared, then it's a right triangle. Well, what if it doesn't equal? So these two theorems tell us what happens then. If that c squared is too small, if it's smaller than the sum of the other two, if the side's too small, that means in the triangle an angle must have been too small as well, and it turns out that triangle ends up being a cube. Or if that third side, the c value, ends up too big, so c squared is bigger than the sum of the other two. Too big of a side must mean we had too big of an angle, which means that that triangle would be obtuse. So the majority of your problems today, you will be given 3 numbers and asked, what kind of a triangle do these make? So our first one, let's say we have 6, 8, and 10. It is important that when you test these Pythagorean theorems and the converse of Pythagorean theorems, that c is always your biggest side. Not the last number listed, but the biggest number listed. Okay? C must be the biggest one. If there's going to be a hypotenuse, the hypotenuse will be the biggest one. So that's what we need to test. So I'm going to say, is 10 squared equal to 6 squared plus 8 squared. So 10 squared is 100, 6 squared is 36, and 8 squared is 64. So I add that up, and 100 does equal 100. So it works. If it works, that means it came from a right triangle. Time saver, this was one of the Pythagorean triples that we looked at. So if you can just look at it and recognize it, then you save all that work. Okay? But it's still possible to do it even if you don't know them. Four, 6, 8. The biggest one needs to be the one that's alone. That's the only one that has a chance of being a hypotenuse. So we're going to say, is 8 squared equal to 4 squared plus 6 squared? 8 squared is 64. 4 squared is 16, and 6 squared is 36. We add that up, and we get 52. 64 is bigger than 52. That means that third side of the triangle was too big, which means there must have been an angle that was too big, and a big angle we call an obtuse angle. I would suggest that when you do these problems, you always put that largest side, the C value, on the left. It works to do it either way. A squared plus B squared equals C squared, or C squared equals A squared plus B squared. Okay? It works either way, but in terms of figuring out if it doesn't end up at a right triangle, if we don't end up having that equals, it will be easier to see the acute or obtuse if your inequality is set up so that the C value is on the left side. Because then 64 bigger than 52, bigger than we think obtuse. Okay? So you will be able to easier see the acute and obtuse situation if your inequality is pointing the right way. And that'll happen if you put the C value on the left. Another example. Eight, 10, 12. The biggest one needs to be the one that's by itself, not necessarily the last number, the biggest number. We're going to test that against the other two. 12 squared is 144. 64 and 100. 144 is smaller than 164, which means that third side was too small to be a hypotenuse, which means we must have had an angle that was too small to be right, and a small angle we call an acute angle. A couple more examples, but are there any questions on these before I clear them?
Is this all the assignment is composed of?
Pretty much. This type of problem.
Shoot. Yeah.
We always need to put the biggest one alone. If you're unsure, because these aren't normal counting numbers, which one is the biggest one, grab a calculator and type it in and get their decimals, and then you'll be able to tell which one's the biggest. We don't actually want to work with the decimals, but to be able to judge their size, if you can't tell by looking at it, it is very important that the biggest one is the one that's by itself. So you would want to just double check that with the decimals on a calculator.
But even with the set of square roots, wouldn't it just be obvious by the number underneath?
If they're all square roots, yes.
Oh.
So if they're all square roots, then yes, you can just look at the numbers underneath. But if some are square roots and some are not square roots, then you might have a harder time putting them in order.
What would happen if there's like the 7 was biggest, but there was 2 of them? Like the base
Can't happen. Good question. Can't happen.
It can't even be a triangle.
It's true. That's why it can't happen. What do I get when I square the square root of 14? 14. When we square square root, they just cancel each other out. 14 is 7 plus 7. This resulted in truth, which means right triangle. One more to look at. So in something like this, you might have a harder time trying to put them in order. So this is where I would say just grab a calculator and type in 4 square root of 3 and see what decimal it gives you. So you can tell that one is bigger or not bigger than 8. 8 is the biggest one here, so we're going to want to put the 8 alone. But if you can't tell by looking at the numbers which one's the biggest one, do make sure to double check that. It's very important that the biggest one is the one by itself. 8 squared is 64. 4 squared is 16. And what do I do to square that other number? What do I need to do to square 4 squared to 3? Square 4 and square the square root of 3. Square both parts. So we square 4 and we get 16. I square the square root of 3 and we have what happened in the previous problem where squaring the square root just goes away. 16 times 3 is 48. And 16 plus 48 is 64. So it works, which means that's a right triangle. Okay. Your homework comes from section 8.3 in the book. You may skip number 15. On number 16, they will tell you that you have a quadrilateral named EFGH for number 16. Make sure that when you draw yourself a picture of that quadrilateral EFGH, you label it going around in a circle. Remember that when we label our letters, we go around, not back and forth. Okay? So you want to pick a corner and start going around the corners. Don't bounce back and forth when you name those letters, or something weird will happen in your problem. You won't be able to solve it that way. You need to make sure that you're naming them around the corners.